Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving here today as it is every day here in my virtual classroom. Step on inside, we're in section 11.5 in the Big Ideas Math Integrated Math 2 textbook on volumes of pyramids. This is a great connection to actually volumes of prisms that we just last did. We also had cylinders, but pyramids are a great connection to prisms. And cones are a great connection to cylinders. And just like prisms and cylinders were a great connection together, pyramids and cones are also a great connection together. So there's this nice adjacency kind of within, kind of two interwoven, kind of mutual friends, if you will, mutual friends. And we're going to find those things. I think it's a shorter section. I think it's only 25 problems. So we'll do the lecture. It'll probably be quicker now that we've seen instances of this, although because now we've identified what a pyramid is. And then we'll do the problem set. We'll see what the problem set looks like there. It's weird that we're winding down as far as the book goes. There are only 3 more sections total. This is 11, 5, 6, and 7. Obviously, I'll do a chapter review, chapter test, things like that. And I think I have to fill in some of the gaps of some of the older chapters. But yeah, you're winding down your IM2 experience if you're watching this and doing the solution guide with me. And if you are doing it with me, you can check the description section down below and find this PDF and download it there, as well as find timestamps for each specific part. If you're trying to find more sections in this IM2 playlist, you can also find that down in the description section below. So guys, without further ado, let's go ahead and get started. And, the way I wanted to get started here, I generally, whenever you guys download these things, you actually start with this front page, and I always delete it because it's more of a class activity thing. But when I saw it, I was like, I can't believe the book's actually doing this. This is a way that I show volume of pyramids as well with things. And then I flip to the next page and say, what do they say after that? They do some derivation stuff. I think you guys will understand this part more. I think it's more important that I speak on what this is, and I want to get to this one. And then the next first page is a little more moot when it comes to it. So we're going to start with volumes of pyramids. How can you find the volume? There's a practical application. If I have a prism and a pyramid that share the same base area and share the same height, there is a ratio relationship between their volumes. You can actually take sand, water, whatever this is supposed to, coffee, I don't know what this is supposed to be, mud. You can take the volume of something. If you could fill up the pyramid with sand and pour it into that prism that has equal base area and equal height, you will have filled up 1/3 of that prism. If you're not sure of that, do it 2 more times. Boom, boom. You do it 3 times total, you fill up that thing. I gotta sneeze, hold on. It's always my bedroom these days, I swear. Okay. So you can fill up, if you have enough sand, you can fill up 3 of these pyramids into 1 of these prisms. What that means is what you think it means, and I'll skip the rest, but what that means is what you think it means. If it's 3 pyramids equals 1 prism in terms of volume, then one pyramid is, I'm going to skip this part. 1 prism is 1/3 of, I forgot what I just said. 1 pyramid's volume is 1/3 of the prism's volume. The volume of a prism is area base times height. Given that you have the same area of the base and the same height for the pyramid, it's going to be 1/3 that amount. So take that, what you did before, and divide it by 3. There are a lot of formulas that are going to be had in this last set of sections. A lot of them. Even the prism and cylinder stuff could have been broken down into many different ones depending on what kind of base you have and if you do it that way. But if you generalize them much more, you are going to be off so much better, especially if you have to memorize them. And I quote memorize because I'm not big on memorizing. I'm trying to get you to contextualize what these ones are. Now, the important part of height is the perpendicular bit to your base. It goes up to the apex, but from the base perpendicularly. It is not this one. This is what's known as a slant height. We're going to be getting into that later when we talk surface area of pyramids. I'm sure that comes up in a section or two. I think the next section probably. If they do them, I actually don't know which ones they do. For sure they'll do it in IM3. But if you have an oblique pyramid, the height is on the outside because it's still going to be perpendicular to your base. So it's whatever distance that thing is, that's your height right there. Okay, let's go into the examples. Let's find the volume of this pyramid, shall we? We have a triangular pyramid where the area of the base, we can do 1/2 base times height of the base, that is, because these parts are perpendicular to each other. And that's the same thing, height perpendicular to base, even for the base itself. So 1/2 base times height is the area of the base of the triangle. That's going to be 12. The height of the pyramid is 9 meters. So we multiply area base times height, and we take 1/3 of that. Apparently it calculates to 36. I'm going to trust them. 36 cubic meters is the volume of that pyramid. Now a prism a triangular prism that would have had the exact same area of base and height would have been 108 cubic meters, 3 times as big. But this one is not that. Okay. More volumes for them to do, but keep in mind this is the height here. There's a regular hexagon we'll have to do. There's square pyramids, things like that. Remember, the name is based off the base. Most of them, I believe, they're going to have on the bottom. They could also flip it over. It doesn't matter which way it is. Whatever the base is, it's that one unique one that's not the triangles, unless it's a triangular pyramid. But they'll help you out. All right, second example. It's a word problem. Originally, Khafre's pyramid had a height of about 144 meters and a volume of about 2.2 million cubic meters. Find the side length of the square base. So we did some of the stuff with prisms before. You know the volume, you can substitute it. It's area of base times height, and the base is a square. So both the side lengths, I would just find the area of the base first, then determine what kind of shape it is, and then go from there. But the height's 144, take a third of that, etc., etc. First thing they do is a good one. Multiply both sides by 3. If you can't divide 144 divided by 3, and you can, it's 48. But if you can't divide it by 3, multiply both sides by 3, then divide by the 144, then take the square root of both sides. They're staying approximately the whole time, for whatever reason, I guess because they said about this amount. So from there, we're good. About 215 meters, meters per side of that base, of the square base. I'll probably take care of sniffles here. 1 second. Yes, there was for sure some sneeze aftershock there. All right, third example, find the height of the triangular pyramid. You're given the volume. You have an area of base you can figure out here. 1/2 base times height for this triangular pyramid. And then you do that to find the height. So you substitute everything but height. Basically substitute within your same formula, but then you're just trying to solve for another thing, and they get a height of 7 feet. So I'll let the calculations be what they are. Those examples I'm sure we're going to do more of. Volume of a similar solid. This doesn't change from what it was before. It's still a solid, so whatever corresponding part similarity ratio or scale factor is, the volume is going to be the cube of that similarity ratio or scale factor. So they divide the height of pyramid B to height of pyramid A. They get a 3-to-4 ratio when you do 6/8. So that means that every other length shares that 3-to-4 ratio. That includes perimeters, that includes slant height, that includes length of the side of the base, all that stuff. Surface area, which we're not getting into right now, would be the square of that. You take 3/4 and square it, get 9/16, and whatever this surface area is, this is 9/16 the amount. But volume, you cube 3/4. 3/4 cube is 27/64, which apparently they don't show. And you take 27/64 of this volume to get this volume here, and you get around 40, or exactly 40.5 cubic meters. So you don't need to find the other information out and work that out to get there. Just do similarity ratio, cube it, and set up your proportionality from there. Find the volume of a composite solid. There's no change in what we did from finding volumes before. The difference is now they're adding pyramids into the fold. So I have a cube on bottom. 6 cubed is 216. They actually do the same thing. That's how volume of cube works. And then they add the volume of this pyramid up top here. I assume we're going to be doing some subtraction of some as well, but you do that one plus the pyramid and you get a total thing there. I'll let the work again speak for itself. You can pause and check it out. But this has a side length of 6, so does this. In fact, you can use the same exact area of base. Actually, I guess they didn't call this area base because they just did the cubes. But area base here is 36. Area base here is 36. In fact, they both share the same height. You know what this even is even better? This is area base times height. This is 1/3 area base times height, but it's the same area base times heights for both. So there are ways to do that. Anyway, 288 cubic meters. They call this a composite solid. I can't tell how this is a composite. I guess, is that a pyramid on top? I can't tell what this shape is doing up top. If that's a triangular pyramid or something, or if it's cut into it. I'm glad we're not doing... Oh, I see what it is. I got it. So I got a triangular prism on bottom. I see it. Triangular prism on bottom like that. Sort of, whatever. And then up top, we have a triangular pyramid there. I see it now. I see it now. So yeah, add one and then add the other, and we're good to go. Hey guys, we're going straight to the problem set from there. So less than 10-minute lecture. Awesome. I think this is going to be going very swimmingly. Just take a third of the area of the base times the height. You get the volume. So yeah, that's what they're saying here. Explain the difference between a triangular prism and a triangular pyramid. I think they're really speaking in terms of volume. And what we can say is the volume of the triangular pyramid is 1/3 the volume of the triangular prism. Because what's the same? Because what else is different? One's a prism, one's a pyramid. But what's the same about them? Well, we don't know if they're the same base and height and all that. But if they did have the same ones, then that's how it works. I don't know if that's what they mean. Assuming same base and height. They're just talking about difference between, because there are other things we can say, right? Triangular prism has 5 faces. A triangular pyramid has 4 faces. A triangular prism has 2 bases, but that's the same with all prisms. And a triangular pyramid has an apex height, and that's the same with all pyramids. So it's just, I don't know, it's kind of hard to say what else we can state there. A square pyramid and a cube have the same base and height. Compare the volume of the square pyramid to the volume of the cube. So, this is where I would probably say this here. So I don't know what they really wanted to say up top. So the volume of the square pyramid is 1/3 the volume of the square prism of the cube. Assuming, not assuming, they told us that it is. So yeah, I don't really know what they wanted us to say for the first one. I mean, a triangular prism is a prism. Triangular pyramid is a pyramid. Both with the triangular bases. So I probably have a wrong answer for the first one, but I stated some other things out loud I hope you can read into. All right, guys, we're going to get started in this problem set. You might want to grab your calculator as you could see the different kinds of things we're going to do. I forget how they rounded. I'll just do nearest 2 decimal places if that's easiest for you. Not many things in terms of pi, though, so maybe there's not really many, if any, rounding that we actually have to do. We do have to divide things by 1/3. Divided things by 3 often, so I'm sure there's something there. So guys, I'm going to go ahead and get started with this thing. We are going to jump into problems 3 through 25. We start numbers 3 and 4, and we find the volume straight up. No classification. They are pyramids. Let's go to war. Number 3, we have a rectangular pyramid. Rectangular base, where we're going to, again, volume is 1/3 area of base times height. So area of the base is 12 by 16, which is 192 square meters. And the height is that perpendicular distance, which is 7 meters. So the volume of this thing, we'll do 1/3 area of base times height. And this is where I start to get a little clever. 1/3 of 192, I think, is 64. So I'm going to work smaller first if I can, and then do 64 times 7. I think that's 462. Is that right? No, wait, no. 448. 448. I was thinking of 66 times 7 or something. I don't know. 448 cubic meters. I'm going to trust that because I did all that in my head. I haven't whipped out my calculator, so I think I'm going to have to whip that one out pretty soon there. So that was the volume for that one. That's number 3. Number 4. Number 4, let's do this one. And this one's appearing a little, it's not oblique. Well, it is oblique in that it's not right in the middle there, but we got a right triangle base, and then we kind of have like a right pyramid, but that is the height. The height is 3 inches there. The height of the base, though, would kind of be 4 inches there. So number 4, the area of the base, we're going to do 1/2 base times height, which is going to be 6 square inches. And then the height of the pyramid is 3 inches, as it is perpendicular to your base. So the volume of this guy will be 1/3 area of base times height, which I think 6 cubic inches for that guy. So I don't know how much we'll need the calculator, I guess, all told. You know, there's some things here and there that we might have to work with, but otherwise, that's looking pretty decent there. So we got 448 cubic meters and 6 cubic inches for the first two. And then we kind of get off that. So now we have numbers 5 through 8. I never switched this over. I apologize. Now we have numbers 5 through 8 where we find the indicated measure. We're going to find the side length. So they're jumping off the volume stuff right now. They said you did a lot of practice last time. We can go here. A pyramid with a square base has a volume of 120 cubic meters and a height of 10 meters. So if I were to do a nice little drawing of that, what I would do is kind of like that. There's my square base. And from the middle, I'd like to draw a height up there. So I'm going to connect those after that. I'll practice my drawing on that later. Has a height of 10 meters. 10 m. 120 volume, find the side length of the square base. So these are both unknowns with x's. Remember the area of the base is x squared. So Going into this, volume is 1/3 area of base times height. So the volume is 120 cubic meters. The height is 10 meters. And of course, we have the area of the base written there. So the volume, 120, equals 1/3 this area of base times height. This is where I'd like to multiply by 3 to begin with and get 360. And divide both sides by 10 and you get 36 for your area of base. Now, area of base is also that x squared. So x squared is 36. Take the square root of both sides. You get plus or minus 6. But as you know, we're referring to just positive units here when it comes to lengths. So 6 meters for the area of the base of number 5. Number 6. Pyramid with a square base has a volume of this and a height of this. So it's the exact same setup as before. I'm not going to draw anything this time. I'm going to jump straight into this fold right here after I write these. We got a volume of 912 cubic feet and a height of 19 feet. So no difference. This volume, 912, is 1/3 area of base times height. And because I can't take 1/3 of 19, I'd like to go and triple this, where you get 2736 equals 19 times area of base. I don't know that number, so it's my first calculator whipping out here. 2736 divided by 19. And we get 144. So area of base is 144. That means that x squared, they said find the side length. Yeah, it's the same exact kind of question. So if your teacher gives you one and the other straight up, I think you're good to go. So x is the square root of that. We're talking 12 feet. This was square feet better. 12 feet for side length. All right, let me get a tissue. Give me one moment. Okay, we finished 6. Jump to number 7. A pyramid with a rectangular base, so not a square base, has a volume 480 and a height of 10. The width of the rectangular base is 9. Find the length of the rectangular base. So, okay, I'm not going to do as many drawings if not really needed from this set, but we do have volume as 480 cubic inches. Height is 10. Now, the area of the base, we know, well, we don't know, we're trying to figure out, but the area base, we do length times width, right? The width is 9. We need to find the length. So width times length, 9L, will be that setup. You can plug this into the main formula part, but I like to kind of just get B by itself first and substitute. It's your call. But the way I say this once again, volume is 1/3 area of base times height. If there's one silver lining in actually doing the 9L, here, let me do it for this problem. If there's one silver lining doing the 9L, and honestly, they might have set it up for the other, well, no, the other problems, you didn't know the numbers. But if there's one silver lining in using this is instead of multiplying both sides by 3 here, I can divide the 9 by 3. If I divide 9 by 3, I get 3. It doesn't change my goal of solving for L. So, and I can do 3 times 10 here and get 30. So 480 equals 30L. So I see promise to that. You don't get the area of base at all. I didn't find out what it was first. I can find out second. If you divide by 30, it looks like you get a length of 16 inches. And I've said this before in videos. I don't know if it's one of these ones or like these IM2 Big Ideas Math things or something else. I learned out very late in life and through tutoring like a 7th grader that length is always, because I didn't know how to equate length versus width and how to state how you identify one versus the other. The length in a rectangle is always supposed to be longer than the width, apparently. And that's something I learned much later in life. It's like 3 years ago or something. All right. It was like 6 years ago. Number 8, a pyramid with a rectangular base. Height. Okay, so it's like the other one, only this time you're given the length and find the width. So you have a volume of 105 cubic centimeters. You have a height of 15 centimeters. And that one I can divide by 3, so I'll be good there. Area of base is length times width. The length is 7. We're trying to find the width. So the volume equals 1/3. I'll just put B this time. Area of base times height. The height, I can do 15 divided by 3 and I'll get 5. Okay, so 105 equals 5 times area of base divided by 5. You get 21. That's 21 square centimeters for area of base. Now, in finding the width, we can say, boop, based off these two here, area of base is 7 times the width. Therefore, width is 3 centimeters. It's So there's the work. Yeah, I don't think drawings are really needed for those ones based off construct if you understand how rectangles work. I mean, they say the thing straight up, and we can just identify them, label. We're good. All right, got an error analysis on number 9, perhaps on number 10, but it's not on this page. Describe and correct the error in finding the volume of the pyramid. They do 1/3 6 times 5. They got 6 as one of the base edge lengths, but they never found the area of the base. This might be the base for the base, like a base at, like a base times height kind of thing for the base, but they have to find the whole thing. So on this one here, give me 1 sec. I got a text I got to respond to. Okay, sorry, I'm back. I don't know what I got to say or not, but I noticed that I'm on my text thing, so apparently I'm ready to type. So I think I mentioned that the problem was they only used a base edge, not the entire area. So in their formula, they only used the base edge and not the base area. So we got to correct it. That's big typing. So we got to correct it here. Volume is going to be 1/3 area of base. I'll just put it straight in here. This is a square, right? So 6 squared times, let me put it this way. 1/3 of 6 squared times height. There may be an urgent need for, this doesn't matter to you because I paused the video. Obviously, I have the time to delay things, but I may hit little pauses. There are important text shooting back and forth right now. Anyway, 1/3 of 36 happens here. Or listen, we can do 36 times 5 and we get 180. And then 1/3 of 180 is going to be that 60 is what we're looking for. 60 cubic feet. And that should be the answer there. Okay, so now we move forward to number 10. Okay, in number 10, open-ended, give an example of a pyramid and a prism that have the same base and the same volume. Explain your reasoning. So what we'll need is, they didn't mention height. What we get to do is vary our heights. So say we had, same base. I'll do like square bases for these things here. I'll make this one the pyramid. So I'll kind of put this one up like that. Square pyramid here. Now, the square prism, remember, a volume of a pyramid is 1/3 the volume of a prism. If you get a prism that's 3 times smaller, then they cancel each other out in that way, right? They kind of had a drawing of one of these in the initial page of what we had in our notes. If we take a whole base, a whole prism with that same height, but we divide it by 3, right? So we just get it down to here. So that would be an example of this that we're looking for, where it's like, like that sort of. So if this is height, I don't know if it says give an example. So, okay, if this height was 12 whatever units, then this height would have to be 4 units here, right? And then if I have this is like 10 and 10 and 10 and 10. So if you see what's going to happen here, the volume of this prism will be 1/3 area of base times height. 1/3 of 12 is 4. 4 times 100 is 400. You get 400 square or cubic units. And this one, volume of this is area of base times height. Now this area of this base is 10 squared, and this height is 4. 100 times 4 is 400. 400 cubic units. Because we took 1/3 of the height, it's like when I said, remember the first thing I said? 1/3 of 12 is 4. So that was that first thing that's going to match up with that guy there. And explain your reasoning. I kind of did, but let me just say it again based on this. Make the prism have a height that is 1/3 the height of the pyramid. 1/3 the pyramid's height. To counter the pyramid's volume being 1/3 the prism's volume. A prism's volume of the same height. I typed PFT. Pfft. 1/3 the prism's volume. Pfft. All right, number 11. 11 through 14, find the height of the pyramid. So they give you volume. It's a lot like the ones that they did before when it came to the other examples. Only this time we find height, not base stuff. These would arguably be easier, I believe, than like numbers 5 through whatever. So our volume is 15 cubic feet. Our area of base is, in this case, a square pyramid. So 3 squared, that's going to be 9 square feet. And then the height is unknown, right? We're trying to figure that one out. So volume 15 is 1/3. Area of base times height. 1/3 of 9 is 3. 15 equals 3h. Divide by 3, you get h equals 5. I haven't had to use my calculator very much, even with these 1/3 bits. So 5 foot height for number 11. Number 12, yeah, these ones kind of seem easier than the ones before, especially because you have the drawing this time, right? So number 12, we have a volume of 224 cubic inches. We have area of base. It's a rectangular pyramid, so 8 times 12, which is 96 square inches. Unknown height. So the volume equals 1/3 area of base times that height dough. 1/3 of 96 is 32. I don't want to put 32 there, though. Equals 32 times the height. Divide. Is that 7? Height is 7. 7 inches. Number 12. Okay. Number 13. Triangular pyramid. In this triangular pyramid, that height is unknown. We have the volume as 198 cubic yards. The area of the base, this is a triangle this time. It's a right triangle, though. So we get to do 1/2 base times height of the base. The base 11, height perpendicular to that is 9. Now, this is not an integer. Half of 99, well, 99 over 2, but it's also, I believe, 49.5 square yards. Height being unknown still, the volume is going to be 1/3 area of base times the height. I don't know 1/3 of 49.5, so I'm going to triple this, and I get 594. And I can only imagine this is an integer. It must be, not 6, 12. Because 99, yeah, I'm going to say that's 12. I'm going to go ahead and check that with a calculator. I assume we're just doing whole numbers there. Calculator. So 594 divided by 49.5. Yeah, getting 12. So I think everything else was correct with what we did there. So that'll be 12 yards. Always have the units. Do not forget the units. Don't forget the units. Number 14. Yeah, these problems are Volume is 392 cubic centimeters. Area of base, also a right triangle. They're really not challenging you with the triangle things here. 1/2 base times height. Half of 14 is 7. 7 times 7 is 49. So you get 49 square centimeters. And with an unknown height. Let's jump into it. The volume equals 1/3 area of base times height. 1/3 of 49, also not kind of a clean number there. So let's triple 392, and that'll be 400 minus 24. So 776. And I'll only trust that if I get an integer answer here. If not, I will not trust that. No, wait, hold on. That is not right. That's not 7. It's 1176. So that wouldn't have been a good one. 49 times height. Let's divide by 49. I'm going to guess, 50 times what is 1200? 24? Wait. 24? So I'm going to guess this is 24. I'm going to check that as well. 1176 minus, or divided by 49. 24. All right. Hey, there's some good math there. Except when I said 776 for the other part. All right. Numbers 15 and 16, the pyramids are similar. Find the volume of pyramid B. In this case, it's smaller. In this case, it's larger. But we have corresponding side lengths, or lengths, I should say, in this case, heights for number 15 as they correspond, we can see that the ratio, the similarity ratio from A to B, let's do B to A, is 3 feet to 12 feet for those heights. That is a 1 to 4 similarity ratio. So the volume ratio, we are going to take that 1/4 and cube it. 1/4 cubed is 1/64. So the volume of pyramid B is not 1/4 the volume of pyramid A, it's 1/64. And I know that's weird to hear. There's something else I want to do with this later. I'll probably do it when I talk about cones, just because of the shape of it. But there's something else that you got to hear, that even if you can't wrap your head around this one, which it's true, there's another one that even with less discrepancy that I think you won't be able to wrap your heads around. Anyway, volume of pyramid A is 64 times larger than volume of pyramid B. So you're going to take 256 divided by 64. But if you want a setup of that, we're going to say whatever this B to A is in terms of volume, 1 to 64, then this B to A is B, volume of B, and volume of A. And that's cubic feet. Multiply both sides by 256, you get exactly that. Volume of B is 256 over 64, which is 4 cubic feet. Now, there are other ways to do that if you want to divide the heights by 3, but if I gave you something else that you couldn't discern, that's the way that you're going to go about it, and you should go about it that way. All right, number 16, we'll find the volume of pyramid B in this scenario as well. We have corresponding side lengths of similar pyramids, 3 to 6 or 6 to 3. Let's do it kind of in a faster way. The volume ratio will be taking 6/3 and cubing it, which is 2 cubed, which is 8. That means the volume of pyramid B is 8 times larger than the volume of pyramid A. Pyramid A is 10 cubic inches, and you multiply by 8, so you'll get 80 cubic inches. Yes, they can be done a lot faster with that in mind. You might be asking, how do we know which one to divide? Do we make it bigger? Do we make it smaller? Do we go from B to A? It doesn't matter. As long as you correspond, you go in proper direction when it comes to corresponding parts. Volume of B was smaller than volume of A, so I got to tie the volume of B with the 1 and the A with the 2 with the 64, things like that. So as long as you correspond it right, you know this is supposed to be bigger, so the multiplying by 8 is supposed to happen. Kind of like that. Okay. Number 17 through 20, find the volume of the composite solid. So this is where I start to organize my work a little bit differently here, where I start to say, let's call this object 1 and object 2, find the volumes of those separately and either add them, subtract them, depending on what the nature of the solid itself is. So this number 17, and I want to clear out that 17 that you see there. So on this 17, okay, I'll call this object 1 and object 2, or figure 1 and figure 2. They have the same area of base. So when it comes to me doing area of base, guys, I'm not going to say B sub 1, B sub 2. They're the same. They're the same. They're rectangles. We got 4 times 6. We have 24 square inches of base area, no matter which figure we're talking about. Now, the height of figure 1 is 3 inches. So when we find the volume of figure 1, we're going to do, it's a pyramid, we're going to do 1/3 area of base times height. 1/3 of 3 is 1 times 24 is 24. So we get 24 cubic inches of volume for object 1. Object 2, the height of this one is 2 inches. Not 3, but 2 inches. So the volume of object 2 is, it's a prism. Area of base, let me write that again. Area of base times height, which is 48 cubic inches. So we have both of these, worked out. Now let's find the volume of the total. We will be adding them. We saw a lot of these in, or a few of these, a handful of these in the last section. So we're going to be adding the 24 with the 48, and we get 72 total cubic inches. I'm really a fan of so far, we're not doing things in terms of pi. There haven't been, regular hexagon things and things like that. So we haven't had to do root 3s and trig and pi and stuff like that. So it's been kind of nice to not have to round. I guess that's why I didn't know what to round to, because I don't think they had to before. All right, number 18, we have a triangular prism and a triangular pyramid. They both share the same area of base. Keep that in mind for number 18. So I'm going to start off with that area of base. I don't think I'm going to copy this one over this time. I think it's decent enough with what we have. figure 1 and figure 2. So area of base, it is a right triangle base. They're being very nice with you on that. 1/2 base length times height length of that bottom. Notice the bottom I'm pointing at here. Half of 12 is 6, and 6 times 9 is 54. So 54 square centimeters for area of base of either object. The height of object 1 is 7 centimeters. So the volume of object 1, we take 1/3. It's the pyramid. We take 1/3 area of base times the height. 54 divided by 3 is 18. And 18 times 7 is 136. And I apologize if I'm getting anything wrong. I'm not using my calculator for a lot of these things. So sorry if I get something wrong. I hope my setup is getting you to where you need to go. Truly. The height of object 2 is 10 centimeters. That's the prism. That's the prism's height. And the volume of object 2 is area of base, 54, times height of 10, which is 540 cubic centimeters. And these are also added together when we find the volume of the total. So the volume of the total, we'll get 136 plus 540, which is 676 cubic centimeters. Okay, that's number 18. Let's jump to number 19. They're two pyramids, and they're congruent to each other. So whatever the volume of one pyramid is, I'm going to double it. How do I know they're congruent? They're by reflexive property. They share the same base, right? Literally, that are congruent. And then the same heights. One's underneath, one's inverted. It's an upside down version, but they're the same thing. So the volume of the total equals 2 times the volume of either pyramid. So let's just find the volume of that pyramid and then double it, or whatever. In fact, volume of a pyramid is 1/3 area base times height. Let's just do 2/3 area base times height. Boom. Okay. So let's find the area of the base. It's a square base, so we'll do 8 squared, which is 64 square centimeters. And the height looks to be 5 centimeters for either. You could double it and get 10 and such, but you have to make sure that you get how that would double up as a whole. So the volume will be 2/3 area of base times height. And I'll be honest, neither of these numbers divide by 3. So this is going to leave us with one of those things that we have to round. I'll go more in the conventional kind of exact fraction first, and then we'll go ahead and divide it by 3. 64 times 5 is 320. And 320 times 2 is 640. So we get 2 times 5 is 10. So 640 over 3, and that's in cubic centimeters. So that's an exact answer. If we are to round it, what is that? 213.33? That's right? 13, I think so. So 213.33 cubic centimeters for number 19. Number 20. So now we have one where we have to do a subtraction. Notice how the pyramid inside is being kind of removed from this cube. And it is a cube there, so we get to cube the 12s. I forget what 12 cubed is. I should know. But we'll call this object 1, and the pyramid we'll call object 2, if that's cool. So the volume of object 1 straight up, let's go right into it, is going to be 12 cubed, which is, I don't know, 12 cubed, 1728. I don't remember that. That doesn't even ring a bell. It doesn't register. Maybe I never did know it. Maybe I was thinking of the 11s. Volume of object 2. Here's the thing. They didn't give us any lengths of this thing. Obviously, the height is what it is, right? The height is going to be 12 inches. It's the same as the prism. But they didn't give you lengths of these other guys. But they did mention congruency here. So what you're seeing from like a top-down view is you do have a square. You can tell you have a square because it says 12. So you have a square. This is going to look from the top down. And for the pyramid, we're looking inside of it like that. It's basically a square inscribed inside a square. And what's happening is it's dividing these up. This is 6 and this is 6 because they add together to make 12. That's a right angle being a square. And these are this it looks like a rectangle. I thought it was a rectangular pyramid. It must be a square pyramid based on everything being congruent. So this is 6 root 2. So it's a square pyramid with these being, all that, right? These being congruent. So when it comes to the area of the base of the pyramid, area of the base is 6 root 2 squared. And 6 squared is 36, root 2 squared is 2. So you get 72 square inches. So that's the area of the base. When we find the volume of object 2, and this is object 2, volume of object 2, it's going to be 1/3. 1/3 area of base times height. 1/3 of 72 is 24. 24 times 12 is double 12 squared, so 288. 288 cubic inches. So we have the volume of object 1, the volume of object 2, and we are going to not add them, but subtract them. So 1728 minus 288. Well, ends in a 0, whatever that is. I don't want to be wrong, but it looks to be 1440. Ugh, I don't want to be wrong. I'm going to check that. 1440 cubic inches. Where are we on this guy? Sorry, I got lost in my stuff. Okay. Number 1728 minus 288. Yeah, 1440. All right. I'm going to go with it. If you're cool with it, I'm cool with it. It's A. It's whatever. All right. Number. Where? I lost. Whenever I pop up my calculator, I lose the stuff. I know I didn't even go to the calculator for you to see, but whenever I do, I lose where I am. So I found it. Number 21. A pyramid has a height of 8 feet and a square base with a side length of 6 feet. They don't say draw it, but I'm going to draw it. A square base. We've done a lot of those. Sometimes better looking. Side length of 6 feet, height of 8 feet. So we have that there. Okay. All right. Looks good, doesn't it? Part A. How does the volume of the pyramid change when the base stays the same and the height is doubled? Well, the volume's going to double. They don't ask me to explain it, but the volume will double. The only thing, there's only one dimension that's changing. Only height. It's literally like taking, again, volume is 1/3, in this case, area of base, times height. Well, if height doubles to 16, if height doubles, I'd literally just do times 2. You're going to take everything and just do times 2. I mean, it doesn't matter what it actually is. The fact of the matter is you double it, the volume will double. So part B, how does the volume of the pyramid change when the height stays the same and the side length of the base is doubled? You have to remember that the sides are, listen, maybe we should calculate these, but the sides, the base is a square. So if the base is a square, both sides have to double there. So let's actually do some of these, but I'll show you kind of how that changes. It's going to be different. I'm going to tell you now the volume will quadruple. Hopefully we can recognize that, why that will be in a moment. If not, let's go ahead and actually do them. So volume here is 1/3 area of base times height. That's 36. A third of 36 is 12. 12 times 8 is 96. So 96 cubic feet for the original volume. In this one, we're going to do 1/3 area of base times height, which will get doubled. So we double this result. You double 96 and you get 192. In this one, why will it quadruple? Well, here we're going to do 1/3. If you double the 6, you get 12, but 12 gets squared. There are two 12s that are multiplying, so it's like times 2 times 2. That's why it's going to be 4 times bigger. And then times this 8 here should get us, what was it, 96 times 4? 384? Oh, duh, double 192. 384 cubic feet. So there's that one. Part C, are your answers to part A and part B true for any square pyramid? Explain your reasoning. Yes, because it's still three-dimensional aspects here. Yes, the only difference between a prism and pyramid is the 1/3 factor, which can be applied at any time. Otherwise, these are simply three-dimensional solids with the same concept of dimensionality and similarity ratios. That if you double 2 dimensions, you're going to be quadrupling your thing as a whole versus 1. All right, number 22. How do you see it? The cube shown is formed by 3 pyramids, each with the same square base and the same height. Is that a... Oh, they called it a cube. I thought this was the top of a pyramid, like a hexagonal pyramid or something. They called it a cube. Okay, I got you. So square... Okay, so they have... Must be... Oh, they said a square. The bottoms are connecting together, I guess. I'm trying to see the yellow for what it is. I guess the yellow one has the base, the square base on the outside. So the yellow one's square base is like... I probably shouldn't overlap colors, but the yellow one's square base is like that. If you can see that, I should probably not use those colors. Yellow base is probably like that as a square. The blues looks to be internal, though. The blues is like, there's another base edge there that's connected, and the square is like out here. I'm not drawing that one right. And the red, I feel like you can see the red square base kind of like that, if that makes sense. So I'm trying to imagine the blues now suddenly, and it's not coming together. Anyway, how could you use this to verify the formula for the volume of a pyramid? Well, it takes 3 of these to make one of those, but where's the height? Well, the height's that yellow part, right? But does that make that a square, though? I guess they're oblique square pyramids. I don't know if that makes sense for me to say it, but they all have the same base and height and the same volumes of each other. So it's going to be 1/3 the volume of the prism. So I think that's how I'm just going to say it. It's just pretty much straight up. I thought they wanted me to calculate some things within there, but they just said, how do you see it? This is a how do you see it question. So the 3 pyramids have the same base and height as the prism and the same volumes as each other. So each is 1/3 the volume of the prism. I mean, there are more hands-on ways that I think that students would be able to do the thing, like pour sand or water or whatever from one hollow prism pyramid into a prism 3 times, and then they kind of get it. And that's as long as you have something to get, right? There's a formula, but as long as you have something to get as to why, I think that's the most important part. All right, I think we have 3 more questions here. Are we going to finish within... We got 12 minutes till the hour. What can we do on the last 3? Let's stop sneezing and stuff, shall we? Number 23. Find the volume of the regular pentagonal pyramid. Round your answer to the nearest hundredth. In the diagram, measure of angle ABC is 35 degrees. Oh, because we got to find the height as well. So let's start with the pentagon base, shall we? I just, 1/3 area base times height, one thing at a time. Let's work this thing out. So with the pentagon base, it's they said it's regular. So I'm just going to work off the bottom, 3 feet. Well, actually, let's write it on the side because I'm going to split up the bottom. So we're going to do as we've done with pentagons before, regular pentagons. Let's split up this thing into apothem and central angle. Central angle is this whole thing, 72 degrees, 360 over 5. Divide that by 2, you get 36 degrees. We know this gets bisected. The 3 feet becomes 1.5 here. So to find apothem, we're going to use tangent. Tangent of 36 is opposite over adjacent. So A is 1.5 over tangent of 36. Now the perimeter is straightforward. That's 3 times 5, 5 sides, 3 feet each. That's 15 feet. So these are exact portions for that. The area of the base is 1/2 apothem times perimeter. Not clean numbers. Let's do what we can with these though, shall we? I'm going to turn 1.5 into 3 halves. Let me do this. 1.5 is going to be 3 halves. Let's only work with fractions and things for now. So we got that. So 3 times 15 goes on top and you get 45. I have 45 over, and 2 times 2 is down bottom, 4 times tangent of 36 degrees. Here's an exact area of base in square feet. We're going to do 1/3 area of base times height, but we still got to find the height. Now, one other thing that's missing here, if you notice this ABC, I know they mentioned the 35 degrees, but what we also have to do in figuring out that height is we need one of these other lengths. I might not be able to find out this length here. Remember, this is going up to the top, to the apex. That is not this thing right here. In fact, this thing is right. Let me color code this. This is right here. This is that length BC. That's this length there. C is the center. B is one of the vertices. We still have to find that. Let's call that R for radius. That radius can be found using sine. The sine of 36 equals opposite over hypotenuse. So hypotenuse is 1.5 over sine of 36. I feel like we should be in the camp of fractions again. What am I going to use this for? Oh, I need to find the height. Oh, this is going to be a little trippy here. For the sake of consistency, I'll call this 3 halves again, but I don't know if it's going to matter much. This is going to be a little bit different, right? So what we now have is this right triangle ABC. I'm probably not going to finish in the hour. Right triangle ABC, and from B to C is 3 over 2. This is going to be a nightmare to type in the calculator. I'm going to be able to do it just fine. Oh, I have to change my calculator to degrees. It's in radians. Give me 1 second. Because it defaults to radians. If I'm going to screw one thing up, I don't want to screw that part up and go, oh, I got a negative answer. What happened? They did say this angle B area is 35 degrees. And y'all, we need to find out this height here. This is the pyramid's height. So we get to use tangent again. So tangent, this is going to look very weird. Tangent of 35 equals h over 3 over 2 sine of 36. Now there's an easy way to write that if we kind of multiply both sides by the reciprocal. Excuse me, this is the reciprocal. But if we divide that thing out, shoot, now I need to write it correctly. Let me make sure I have this right. If you're dividing by that, then you're multiplying by its reciprocal. So that's h times, I need to see it as multiplication, h times 2 times the sine of 36 all over 3. So now you multiply by its reciprocal. Now 3 will go on top here. So h is 3 times the tangent of 35 over 2 times the sine of 36. So I think that's the complete bit. So I have this area of base. I have this height. We got to do 1/3 area of base times height. So we're going to have, and there's nothing here that can cancel or anything, by the way. It's not that kind of thing. Even if there, unless there was a sine of 36 on top and bottom. There's tangent of 36 and tangent of 35. It won't work like that. Volume is 1/3 area of base times height. Now I could type this in the calculator. I'm going to try and clean up a little bit that I can. It's not going to be much. It's really not going to be much, but I want to get rid of some parentheses, all that kind of stuff. I'm going to take 1/3 of 3, and those will go away. I'm going to do 4 times 2 on bottom and get 8. And so now I'll have on top 45 times the tangent of 35 degrees. And on bottom, I should have 8 times, I'm going to put the sine first, sine of 36 times tangent of 36. Like that. Nothing there cancels. This will be my computation. I think that's a lot easier to deal with. So in the calculator, we're going to be doing 45 in parentheses. Well, you don't need parentheses, but initiate it probably is going to be helpful. 45 times tangent of 35 divided by, this needs parentheses, 8 times sine of 36 times tangent of 36. And we already had the 1/3 kind of applied in the overall problem. So this then should be what it is here. About, if route nearest hundredth, 9.22 cubic feet. So V is around 9.22 cubic feet. That's what I'm going to land on for myself as my final answer. I have no way of trusting the answers right other than understanding and trusting my own work. I'm just going to go off of that one. seems pretty legit. All right, long problem, good old critical thinking. I like those problems. I know it's a lot of stuff, and I know it takes up time, but it's pretty cool. Yeah, I don't think we'll finish within the hour. At least it's not proofs, but hey. Thought-provoking, number 24. A frustum, I never heard of that, of a pyramid is the part of the pyramid that lies between the base and a plane parallel to the base as shown. Oh, of a pyramid. I was thinking of a trapezoid. So basically, we cut out part of a pyramid like that, right? So this is like a cross-section of it or something. It's a frustum. Maybe I have heard of it. Write a formula for the volume of the frustum of a square pyramid in terms of A, B, and H. Consider the missing top of the pyramid and use similar triangles. Yes, I agree. So, yeah, let's copy and paste this thing and see what we can do off of that. I'm at odds with what I want to do because it's not the top that we actually have, and they give us labels. They said in terms of A, B, and H. Yeah, if there's an invisible top, let's make it visible and see where this would have gone and see what we want to say about it. Because suddenly I'm having second thoughts about what I want to actually say on this. I was thinking one thing and I kind of lost myself on it. So those all meet at the top, like so. Okay. The problem is this height already being shown that we see there. So I don't know if I have to introduce a new variable, and if that's okay to introduce the new variable, or what. The part of the pyramid that lies between the base and a plane parallel to the base. What I'm thinking about is what we would do in a triangle case. In a triangle, if you had something parallel here, right, how these things relate. I'll put like A, B, C, D. How these things relate here when they're parallel. It's not necessarily mid-segment, but A, B, C, D. How A over B equals C over D, like that kind of thing. And I'm missing that top portion, but I'm thinking about how that can apply as far as how many times B is in comparison to A. I'm thinking like that as well. I'm thinking that whatever B over A is, got to think about that one. Think about whatever B over A is. No, I don't think that works that way. Well, H would be over that part. So, okay, here, let's do this. When I'm thinking of this, what I'm also missing, I'm missing other components of even this guy right here. A over B equals C over D. That's all good and great. But what we're actually referring to now is kind of this E and this F, right? It's not A over B equals C over D equals E over F. No, it's A over A plus B equals C over C plus D equals E over F. And I know I've referred to that stuff before. I'm not going to talk about it right now. But that's the concept. We have our E over F going on, and then these parts kind of have these other missing components. So H would be one of those sections that's a fraction of this guy, but I want to write that in terms of the B and the A. I want to think about that, and I don't know what I want to say on it. I want to use some number examples. Definitely going to go over the hour here. Think if B was a quarter of A. If this was 1, if B was 1, because I have to process this in a different way. If B was 1 and if A was 4, A is 4 times larger than B, which means this would be a base of another part, and then this height would have to be 4 times the size. Yeah, because this is a base of its own thing right here. So this H, this would have to be a quarter of that, height-wise, right? So it got 4, or is it a fifth? Let me pause and think, because this isn't helpful for you to listen to me. Let me pause and think about what I want to say with that, because that's how I want to work out this. I want to think of what this height is, how much additional height there is in terms of B and A, how it multiplies with H, and then I'll get to you on what I'm trying to say. Okay, I think I have an idea, but I want to use a temporary variable like an X to explain it. My kind of part of my problem is I'm thinking of this object and I'm thinking of this object as opposed to thinking of this object and this object. These are the similar ones. So let's say I did a 1 to 4 thing, which isn't obviously, these are made up numbers. If I do a 1 to 4 thing, this is 1/4 the length of these, which means I'm talking about 1/4 the length of that. So we don't have that in terms of h right now, but I'll get it in terms of h, and I'll kind of explain that after. And remember, it's not really 1/4, but it is b over a. So if this whole thing, say, was x, then this is 1/4 of x. So this here, h, is 3/4 of x, if you will. So whatever this is 3 times bigger than that, which is 4 minus 1. 4 minus 1. So you got to take out that portion that's there. So that's a minus b over a. So I think that's how I'm going to work that here. So this guy... Wait. So, oh shoot, I have to sneeze. Hold on. Okay, sorry, I'm back. So... I'm going to struggle with this one still. If this is some... I had it and I lost it. If this is b over a, this is a minus b over a right here when it comes to ratios, times x and times x. But x is just some unknown thing, right? I don't think that part's really required for this, but I need to compare those parts when it comes to what? What am I trying to do here? They said, write a formula for the volume of this square in terms of a, b, and h. So if, oh boy, I'm having trouble writing out h here, and I shouldn't. This should be fine. Okay, if a... Hold on, let me pause again. Okay, so my problem is I keep trying to express another variable, but that's because I have this as h and not the whole thing as h, right? Here's what I should be thinking instead, is this. Let's go back to the 1 and 4 example. If this is 1 and this is 4, I stated whatever this whole thing is, you know, I don't know the actual length, but whatever this, if this is 1/4 of the amount, then this is 3/4 of the amount. That's what I said, right? So if this is some sort of, if this is to that 1, oh, I just had it, then this is b, a minus b amounts of that. If this is b amounts of it, this is a minus b amounts of it. I think I have to multiply, because that's 4 minus 1. I think I need to, this is a minus b times larger than whatever this number is. How about that? This is a minus b times larger of whatever this number is. So h is a minus b times larger, like 3 times larger in this case, than this unknown length right here. Let's just call it an x for a moment. Therefore, that height right there, I can write as h over a minus b, I think. So that's what I'm going to call this thing, h over a minus b. I'm screwing this one up in terms of thought, and I don't know. I'm thinking about that. This is very thought-provoking. My mind just isn't in the right space for that. But it should be. Okay, so a minus b times larger. So what do they want? Let's find the volume in terms of a, b, and h. I don't need the 1 and 4 anymore if that is what you're supposed to do. So that means the entire height of the entire thing, we got to take the entire height and then subtract this height out, or this volume out, I should say. Okay, so let's call this object 1 and object 2. So area of base of object 1 is b squared. B times b, it's a square base. And then the height of object 1 is h over a minus b, I hope. So the volume of object 1 is 1/3 area of base. Let me just put it as b squared as it normally was. Area of base times height of that one, which is going to be, this will look kind of weird, but we'll have b squared times h over 3 times the quantity a minus b. And nothing can really cancel there. So we got one answer there. We're going to subtract that out from the volume of this. Oh, this is an object 2 here. Object 2 is the entire because we got to do a subtraction. So object 2, the area of the base is a squared, and this height we have to combine h with h over a minus b. So this is kind of weird to show two h's here, but h plus h over a minus b, which is where you have to multiply top and bottom here by a minus b. Maybe I just had to do that the first time, just multiply that by now because I need the official h. I think that was the problem in the first place. So you have h times a minus b plus h over a minus b, which I can factor out an h, and I get h. If h is a common factor, I get a minus b plus 1. Is that right? Yeah. Wait, hold on. I'm screwing that up, aren't I? H. No, I think that's right. All over a minus b. I don't know if that's helpful, but I do get that. So the volume, well, I don't know if that's helpful. So why don't I leave it as it was? Because I think I have to do a subtraction thing later anyway, so I'll just keep it as that. So h, a minus b plus h over a. Okay, so I already have it written. So the volume of object 2 is going to be 1/3 area of base times height so oh boy, so on the bottom I have 3 times a minus b, and on the top a squared, it could distribute into that. I'll get a squared h times a minus b plus a squared h. I don't really know where I want to go with that. But I'm going to take this one and subtract this one here. So the volume of the total, and there must be something I have to be able to work out that can clean things up. But this is going to take this one. Now, it has a common denominator, I believe. So I think straight up, yeah, it does. Minus b squared h over 3 times a minus b. So straight up, I'm going to go to black again. They all have... I'm going to distribute. Let's see. Why don't I distribute what's there? That's a cubed h minus a squared bh plus a squared h minus b squared h. I feel like there's more that I could end up, because I can factor an h out of here, but I wonder if something else can go out of there. 3 times a minus b. I hope so. They sure know how to mess with me here. H, I'm left with a cubed minus a squared b plus a squared minus b squared. I don't know if anything can factor out of that. You know what I don't know if anything can factor out of that, like a whole, like one of those factor by grouping things. If I factor an a squared out of there, I get a minus b. Yeah? Let's see. Let me keep going. If I factor an a squared out of here, I get a minus b. This is a difference of two squares. That factors into a plus b times a minus b. Yeah, this will help out a little bit. And I get 3a minus b. So, this now has a squared plus the quantity a plus b all is one thing, and a minus b is the other factor here. I feel like I was sneezing again, man. 3 times a minus b. I'll just let it happen if it does. And the a minus b's cancel. So, I'll do it this way. Divided by 3 is also 1/3. I'll kind of get back to that volume thing. I'll put this here. A squared plus a plus b times h. I'm going with that. I don't know if that's right. I don't know if I can fix it, guys. That's the best I can do. I don't know what the relationship there with the a squared plus a plus b thing, kind of how that actually officially works out. But I feel like I missed a b somewhere. I feel like I missed a b somewhere. That's the one problem, because I feel like it's supposed to be one of those things like that. Like almost, one of those kinds of things. So maybe, let's see where I'm maybe missing one, because I don't know where, but there has to be one I feel like that's missing. Because the whole time, I feel like there was a void. There was a void here that should have had... See, I was looking for this. I was looking for that. A squared B, AB squared, I guess. I don't know. I was looking for something that would have actually done its duty that way. And I feel like I'm missing a B. I don't know where. I think it's wrong. Maybe it has to do with my stuff from the jump. Or maybe it's right, but it just doesn't feel right. A minus B, 1/3 area base times height. I distributed here. I subtracted there. Distributed here. Common denominator there. Yeah, I don't know. I think it's wrong. It feels wrong because it feels like there's supposed to be some sort of symmetry and poetry to it. I don't know. I can play with that again if you really need me to. If you're like, hey, what happened there? Fix it. Let's do it. I've worked a long time on that problem, and it's pretty thought-provoking. Not everything I get's perfect, guys. I'm just trying to work through it best I can. I wish I had real numbers to work with. Then I could tell you all the answers there. All right. Last problem. Hopefully I was right. Last problem, number 25. Let me fix these sniffles, guys. I'm sorry. Not the best ending here. Okay, so much for the hour mark. Okay, here we go. Number 25, last question. Nautical deck prisms were used as a safe way to illuminate decks on ships. The deck prism shown here is composed of the following three solids. A regular hexagonal prism with an edge length of 3.5 inches. I think that's the bottom. And a height of 1.5 inches. A regular hexagonal prism with an edge length. Is that the small thing right here? I want to make sure the drawing's right, but I think it's that small thing right there. Regular hexagonal prism with a edge length of 3.25 inches and a height of 0.25 inches. It must be with being that small. And a regular hexagonal pyramid with an edge length of 3 inches and a height of 3 inches. Find the volume of the deck prism. Okay. I almost feel like I have to like redraw it. Just to kind of get you the feeling, get myself the feeling and stuff like that. I don't know if it's going to work perfectly with that. Let me try something here. Will this work? It should. Okay, it does. Oh, but I can't skew it. So let's do a base here. I'll just have to do kind of a dotted backside here. Sorry, I'm going to... okay, let me build this. I'll pause it. Let me build it, and I'll come back. Okay, I'm kind of proud of it. I spent a few minutes on it, but here we go. Looks spiffy, right? So what I think we're looking at... That took a while. So what I think we're looking at here is this. Now I'm going to start labeling it here. Hopefully you can see it for what it is there. The hexagons, by the way. And I'll draw out some hexagons when we have to do the things. We'll call them objects 1, 2, and 3 when we do them. So, three solids. A regular hexagonal prism with an edge length of 3.5 inches and a height of 1.5 inches. We'll call that object 1. That's the bottom one. A regular hexagonal prism with an edge length of 3.25 inches and a height of 0.25 inches. That's object 2. And a regular hexagonal pyramid with an edge length of 3 inches and a height of 3 inches. That's object 3. I didn't know that this actually had a different edge length. Shoot, I might have messed up the top object then. Then I can't see that, why does that have a different edge length? It looks like it has the same edge length as the second one. Then I might have messed up that drawing. Okay, I'll just have to label them for what they are. But that idea is in place of the three different ones that are there. I hope I'm kind of getting that. So we have, let's start doing some labeling. We have edge length of 3.5 inches. Let's use blue. 3.5 inches here, and a height of 1.5 inches. Here we have 3.25 inches, and then this height here is, that's this height right here, of 0.25 inches. And then here, this is supposed to be 3 inches right here, okay? Sorry, I guess it's the same. I drew it the same. And this height is 3 inches as well. Probably not drawn to scale. Okay, so we have 3 different objects. That's what we're dealing with. So when it comes to the hexagon stuff, it's going to take a little bit. But hopefully the concepts of all the things will be the same. Whatever the 3.5 is, the 3.25 is going to do the same thing. The 3 is going to do the same thing here. You could do... Oh, no, they changed their ratios here. I was going to say you could do similar solid things. So in object 1, if we're looking at the hexagon base, that 3.5 with the apothem and radius and stuff like that, if I divide by 2 with the apothem, I get 1.75. Now, with the second object, right here, where you have the 3.25, if I divide this apothem, remember they're different objects, a sub 2 and a sub 1 and all that. If you divide this one by 2, 3.25, you get 1.6125. I think so. And the purple one, it's a length of 3. So when you divide that apothem by 2, you get 1.5. Is that 1.6125? Is that halfway in between? 1.5, 1.6, yes. No, 1.625, not 6125. 1.625. I think the next one is 0.3125. Okay, so there's that. Now, as far as that angle stuff goes, all of these will be the same. They're all regular hexagonal pyramids, so the trig stuff we do will be the same as well. There is some consistency here. 360 divided by 6 is 60, divided by 2 is 30. Oh, we don't have to use trig. These are 30, 60, 90 triangles. So 30, 30, and 30. When it comes to these apothems, remember it's root 3 times larger. Oh, give me 1 sec. Give me 1 sec. I gotta pause this. Okay. So the first one right here, 30, 60, 90, this apothem is going to be root 3 times larger than that one, so 1.75 root 3. This one is going to be 1.5 root 3. And then this one is going to be 1.25 root 3, 1.625 root 3. So they all have that same kind of root 3 thing going, right? Perimeters, we just got to multiply all these by 5, right? So perimeter of the first one is 3.5 times 5. I think that's 17.25. I'm going to do these all in the calculator just to make sure. 3.5 times 5 is 17.5. 1.625 times 5 is 3.25. 3.25 times 5, I think that's 16.25. Yep, 16.25. And then 3 times 5 is 15. So perimeter 1 is 17.5. I'll save the inches or whatever this is later. Perimeter 2 is 16.25, and perimeter 3 is 15. Okay, so what are we doing? We're trying to find areas of these bases. So area of base 1 is 1/2 apothem times perimeter. I feel like I don't want to round anything. In fact, I don't need to. Like, I'll get exact values. We'll just have some decimals with them. So 17.5 times 1.75, that's almost a square of something there, divided by 2 is 15.3125, and there's a root 3 there. So there's area of the first base. Sniffles. Area of the second base. Ooh, green. Area of the second base is 1/2 apothem times perimeter. I don't know how I didn't notice that all of these apothems are 10 times smaller than, or not 10 times smaller, but this 16.25 here and 1 point. Wait, these are hexagons, not pentagons. I multiplied these by 5. Oh, no. Shoot. Let's do that again. No. I'm wasting your time. 3.5 times 6. 3.5 times 6. Is that 21? 21. So 21. And then 3.25 25 times 6. 19.5. Sorry about this. Good thing I saw a connection. I was like, I don't remember that happening in any other hexagons. These are hexagons. And 3 times 6 is 18. Okay, so 18 here. So let's do that again. This is a 21. Oh my gosh, I'm so sorry. What was a quick, I'm like, we're going to get this done in an hour. No. This book knows when it's 25 questions, they go, ha ha ha. We are not going to let you off easy. Those last couple problems are not going to be your friend. 18.375. Okay. I selected green, but it didn't want me to. Area of the second base is 1/2 1.625 root 3 times 19.5. And I'm getting 15.84375. No rounding. And then the third one we get to do 1/2 of 1.5 times 18. Now the savvy version of me would do 1.5 root 3, excuse me. Savvy version of me would take half of 18, which is 9, and multiply by 1.5 and get 13.5. I really should be using a calculator if I got this far in the game, but I'm going to trust it. All right, there's the area of the bases. They all have different heights and such, so I want to get the areas of the bases first because they all have similar aspects in what they do. All different heights and different shapes for some of them. So this is a height of 1.5, so the volume of the first one is area of base times height, 1.5. And we'll get that. 18.375 times 1.5. 27.5625. Oh, this needs a root 3. I'm sorry. Root 3. Okay. Volume 2 is going to be, this is also a prism. 15.84375 root 3 times its height. I think it's 0.25. 0.25, that's divided by 4. So let's do that number there divided by 4. Oh boy. 3.9609375 root 3. I hope I didn't mess anything up leading into this. I feel like I haven't. I fixed that hexagon thing. Volume 3 is a pyramid. So 1/3. 1/3 the area of its base times the height of 3. So that height of 3 is going to cancel out the 1/3. But 1/3 the area of base times height. So glad to see the smaller 13.5 root 3. So we get to add all these things up. Notice the root 3 is kind of in all of them. So when I do the volume of the total, I'm just going to factor the root 3 out. So we're going to do root 3 times, and these numbers, 27.5625. And by the way, there are probably fraction versions of these. There are fraction versions of these that are probably much smaller to write. All right, let's see what this guy is right here. I'm going to go to the calculator and I'll type this stuff out. So just hang tight. So root 3 times, I have 27.5625 plus 3.96. Oh, hold on. I have it as the previous answer. Let me just type previous answer and not mess it up. Previous answer plus 13.5. I'm getting 77.98-ish something. So it's around, if you want to see the actual calculation, I'm getting, how do I pop this thing up? It's around 77.982, whatever. And it's no longer exact. The root 3 multiplied by this thing, so now it became an irrational value now that we're doing that. So 77.98, was it feet? Inches, cubic inches there as the final results of that volume. Find the volume of the deck prism. I hope that was the deck prism that we were trying to find, and that is what I got there. Okay, so guys, with those last couple questions being quite the ordeal, that ought to do it for this one. I feel like I got to sneeze again, but this is Mr. Robinson. Thank you so much for watching. I'm sorry that the struggle was very real at the end. I'm about to sneeze again. Take care. I will see you in the next one.